Today, we're diving deep into a fascinating and controversial subject, the so-called emergent behaviors of large language models. You might have heard news stories about how recent AIs suddenly master skills, like passing high-level exams, writing computer code, or solving complex math problems that their smaller predecessors couldn't handle at all. Is this proof of artificial intelligence crossing critical frontiers, or just our measuring sticks finally catching up? Are these abilities signs of true intelligence, or are they clever statistical illusions? Stick with me as we explore the science, philosophy, and practical impact of emergent behaviors in LLMs, and try to answer, is this intelligence, or merely the illusion of understanding? Let's start with the basics. Large language models, LLMs for short, like ChatGPT, GPT-4, Google's LaMDA, and Anthropic's Claude, are vast neural networks trained on huge swathes of text. In recent years, scientists noticed something strange. As they made these models bigger and fed them more data, new capabilities popped up out of nowhere. Suddenly, the models were able to do things like three-digit addition, nuanced translation, or logical reasoning, when smaller versions had floundered hopelessly at these tasks. Imagine watching a child try to ride a bike. For months, there's barely any progress. Then, in a single day, something clicks. Suddenly the kid is pedaling like a pro. That's what emergent behavior in LLMs looks like. As researchers increase model scale, either by adding more parameters, more compute, or more training data, success rates on certain tasks jump abruptly from near zero to impressive, just beyond a critical point. It's as if a hidden switch gets flipped. Researchers have compared this leap to a phase transition, the way water suddenly turns to ice at a specific temperature. For instance, GPT-3, with its 175 billion parameters, began acing three-digit arithmetic and complex language games only once it hit a certain size. Other models like Google's LaMDA or DeepMind's Gopher show similar jumps. But here's the tricky part. These abilities don't emerge smoothly. For a while, no matter how much you scale, performance is abysmal. Then, there's a rapid spike. This unpredictability has sparked intense debates in the AI research community. Are these emergent behaviors a sign of real intelligence, or are they just artifacts, strange byproducts of how we build and measure these models? To probe deeper, let's turn to some age-old philosophical questions. What is intelligence, and is it necessarily tied to consciousness? Intelligence, broadly, means solving problems or achieving goals across different domains. LLMs certainly tick that box on paper. They generate code, answer intricate questions, compose stories, and even score highly on standardized exams intended for humans. But is this proof of understanding? Philosophers like David Chalmers draw a sharp distinction between intelligence and consciousness. Consciousness is the capacity for subjective experience, the feeling that there's something it is like to be you. Intelligence, meanwhile, is about problem solving, regardless of whether there is subjective feeling involved. This distinction is crucial. An AI can solve calculus problems or debate philosophical topics without any sense of self, any internal awareness of what it's doing. Some classic thought experiments clarify this. John Searle's Chinese room argument, for instance, imagines a person following instructions to manipulate Chinese symbols without understanding their meaning. To an outside observer, the person seems fluent in Chinese, but internally, there is no comprehension. LLMs manipulate sequences of words with astonishing fluency, but does this fluent pattern matching equate to comprehension? According to most philosophers and current AI experts, it does not. This becomes especially important when people start to anthropomorphize these models. Last year, a Google engineer made headlines by claiming that Lambda had shown signs of sentience. Google responded firmly. There is no evidence that any LLM possesses consciousness or subjective experience. Performance alone does not equal awareness, and we should be wary of assuming that impressive language skills mean genuine thought or feeling is occurring behind the scenes. LLMs, as sophisticated as they are, remain fundamentally machines for statistical prediction, not entities with inner lives. But if they're not conscious, how do we explain the sudden, complex skills they acquire? To answer that, we need to look inside the computational machinery, at scaling laws, model architectures, and the nature of the benchmarks we use to judge success. Technically, an emergent behavior is defined when a skill suddenly appears in larger models that was absent in smaller ones. You can actually see this in the data. Performance curves plotting model size against task accuracy show almost flat lines at chance levels for small models, and then, at a certain threshold, a dramatic upward spike. This isn't what we'd expect from traditional scaling laws, which predict steady, gradual improvement as models get bigger. Instead, emergent behaviors are abrupt, akin to dramatic leaps rather than incremental climbs. Several concrete examples bring this phenomenon to life. Take arithmetic. Early GPT-3 variants, with only a few billion parameters, guessed randomly at multi-digit addition. Scale up to the 175 billion parameter version, and suddenly, accuracy leaps to 30%, well above chance. For tasks like the word in context test, where a model must pick the right meaning for a word in a sentence, accuracy holds steady around 50%, random guessing, until you cross a threshold of training compute. Then, the largest models achieve real gains. Adversarial question answering, conceptual mapping, and chain-of-thought reasoning, where models break problems down into logical steps, are all tasks that display this sharp emergence. Other surprising skills, like generating poetry with internal rhyme planning or interpreting phonetic scripts, have also been catalogued in the latest large models. Why does this happen? Some researchers theorize that these jumps are like phase transitions in complex systems. If you increase parameters or data enough, you get qualitative as well as quantitative change. But there's a competing view. Perhaps these apparent leaps are artifacts of how we define success. For example, a model might gradually get better at each component of a multi-part task, but our benchmarks only register success when all parts are correct. From this perspective, the sharp transition is really in our evaluation methods, not in the model's actual internal learning. Recent studies show that when you measure performance more continuously, for instance, judging how many digits out of 3 are correctly predicted in an addition task, improvements are steady. The jump only appears when demanding all or nothing. Another technical twist, architectural choices and training data matter just as much as raw size. All the leading LLMs use a transformer-based structure, which scales remarkably well, but models like Chinchilla achieve emergent abilities at smaller scales simply by being trained on more diverse and higher quality information. Clever prompting methods, giving models hints or encouraging them to reason step by step, can also unlock latent abilities that are dormant under more basic testing. Early interpretability work suggests that at larger scales, internal representations in the neural circuits become more abstract and more generalized, possibly reflecting a richer form of computation. Yet, does this richer structure equate to independent intelligence, or are we again just seeing better pattern matching? With all this in mind, let's turn to the stakes. Why do emergent LLM behaviors matter in practical terms, and what risks and opportunities do they pose? On the positive side, every jump in model capacity opens new doors. AIs that can suddenly write code well enough to power tools like GitHub Copilot mean that next-generation programming and debugging assistance are a reality. Passing high-level exams lays the groundwork for intelligent tutoring systems that can help millions globally. Improvements in summarization, translation, or document analysis find ready use in everything from journalism and law to medical research and customer service. In the real world, emergent abilities allow for rapid innovation without the need for bespoke engineering for every new capability. But on the flip side, these sudden leaps raise serious concerns, particularly about safety and ethics. When you can't predict which new skills will appear at the next scale-up, it becomes much harder to manage risks. Experts worry about surprises. What if a model suddenly acquires the ability to hack websites, generate malicious code, or automate social manipulation, all at a scale and speed no previous system could reach? A widely publicized open letter, signed by hundreds of tech leaders, actually called for a pause on the unchecked scaling of LLMs, warning that unpredictable emergent behaviors mark dangerous territory. Some analysts believe that better benchmarking and continuous measurement tools might allow us to foresee capabilities before they become widespread. But there's a catch. It's not always obvious which metrics to choose or how to spot emerging behaviors before they manifest in unforeseen ways. Real-world tests show that even expert teams commonly misjudge what large models are capable of. In one unsettling case, researchers drastically underestimated how well LLMs could assist in designing bioweapon plans, signaling that dangerous surprises can and do happen. So what should developers and policymakers do? The unpredictable nature of emergent behaviors complicates safety and regulation. Oversight must be constant, and each incremental increase in model size or training data may need close attention. Companies like OpenAI and Anthropic now routinely monitor each new scaling run for unexpected jumps, but as they admit, predicting how soon or how big those jumps are remains more art than science. Rigorous testing, continual alignment research, and robust safeguards must travel hand in hand with technical momentum. Let's step back and summarize. The story of emergent behaviors in LLMs is both amazing and sobering. On one hand, we're witnessing models that master new skills, sometimes overnight, that were unimaginable just a few years ago. These jumps in ability fuel progress and expand the possible. On the other hand, both philosophy and computational theory urge humility. These abilities, as impressive as they are, might not be the same as true understanding. The models may simply be very, very good at pattern recognition, at mimicking the signals of intelligence, without any actual comprehension or awareness. What's clear is that emergent behavior has reshaped the landscape of artificial intelligence. It drives both the hype and the caution surrounding AI's next leaps. For every new powerful tool comes a reminder that we must understand, measure, and manage these systems more thoughtfully. Ongoing research into interpretability, scaling laws, and better ways to capture what's truly going on inside these black boxes will be crucial for helping us use these models safely and responsibly. So, is emergent behavior in LLMs intelligence or illusion? The truth is, it might be a bit of both. The models are smarter, in a technical sense, than anything we've built before. But until we see evidence of real understanding, defined not just by benchmarks, but by deeper philosophical and practical measures, we should treat their dazzling performances with both excitement and caution. As always, if you want to learn more about this cutting-edge topic, check out the extensive research by labs like Anthropic, OpenAI, DeepMind, Google AI, and independent academics. And don't forget to stay curious, think critically, and keep asking the hard questions about the technology that's shaping our future. Thanks for watching, and I'll see you in the next deep dive. We hope this exploration has enriched your understanding of these profound scientific concepts. For more in-depth analysis of complex phenomena, consider subscribing to our channel. Until our next examination of the natural world.